Okay, so now, so this is a level 3 question. So you're given a quartic of this form: x to the fourth minus ax cubed, x to the fourth minus ax cubed plus bx squared minus ax plus b equals 0. And you're given that there are 4 real roots, and you're given a range for the values of the roots. And so we want to find the maximum value of x1 plus x2 times x1 plus x3 times x4 over x4 plus x2, x4 plus x3 times x1. And so first of all, you can notice that this is equivalent to x to the fourth squared over x1 squared times x1 plus x1 times x1 plus x2 times x1 plus x3 times x1 plus x4 over x4 plus x1 and x4 plus x2, x4 plus x3 times x4 plus x4. And the reason this works is that these two terms correspond to these two, and these two correspond to these two terms, and these two terms are equal, and these two terms will have the 2's cancel out, and then the x4 and x1 terms will cancel out with the squared terms here. And so after that, this is just x4 squared divided by x1 squared times, and now the numerator here is just f of negative x1. And that's because the value of f of x, is just equal to x minus x1 times x minus x2 times x minus x3 times x minus x4. And now the denominator here is just equal to f of negative x4 using the same logic. And so after that, well, we can just use this. And so that tells us that, and if we plug it in, f of negative x1 minus f of x1. So all of the square terms are equal, so they cancel out. And these are negatives of each other, so we can just effectively double it. And what that gives us is that f of negative x1 minus f of x1 is equal to 2a times x1 cubed plus 2a times x1. And so since x1 was defined as one of the roots, f of x1 must be equal to 0. And so that just tells us that f of negative x1 is equal to 2a x1 cubed plus 2a x1. And so using a similar method, we have that f of negative x4 is equal to 2a x4 cubed plus 2a times x4. And so that means that this is equal to x4 squared over x1 squared times x1 cubed plus x1 over x4 cubed plus x4. And so now we can divide both the numerator and the denominator by x1, x4 squared divided by x1, x4 squared. And so this is equal to x1 plus 1 over x1 divided by x4 plus 1 over x4. And so the problem wants us to maximize this. And so to maximize a fraction like this, obviously the best way is just to maximize the numerator and minimize the denominator. And so the value of x plus 1 over x for numbers in the range of 1/2 to 2 inclusive. So the maximum is when x is equal to 1/2 or 2. And the minimum is when x is equal to 1. And so the maximum value of this is when x1 is equal to 1/2 or 2, and x4 equals 1. And that gives a value 2 plus 1/2 divided by 1 plus 1, or 5/2 over 2, which equals 5/4. Excuse me for a second. Sorry. So that equals 5/4. And if you want to check, you can find that one possible corresponding value of x2 and x3 is x2 equals x3 equals square root of 10 minus 1 over 3. But you don't have to find this afterwards. And so the next problem. Okay, I should shrink this down. Sorry about that. Okay, it's still too big. Sorry. Okay, so this question. So prove that for every positive integer n, there exists pairwise relatively prime integers k0, k1 to kn, all of them which are greater than 1, such that the product of k0 to kn minus 1 is the product of two consecutive positive integers, or two consecutive integers. Okay, so first of all, if we let the two consecutive integers be a and a plus 1, then we have that k0 times k1 to kn minus 1 is equal to a times a plus 1. A plus 1. And so that just gives that k0 times k1 all the way to times kn is equal to a squared plus a plus 1. And so now we can proceed by induction. And so first of all, we can assume there exists k0 to k. Oh, first is the base case. So the base case, we want to prove it for positive integers n. So the base case is when n equals 1. And in this case, you have two integers which are strictly greater than 1, such that 1 minus their product is the product of two consecutive positive integers. And so if you let k0 be 3 and k1 be 7, then 3 times 7 minus 1 is equal to 20, which is 4 times 5. And so this is one possible pair for the base case. And now the inductive step is the inductive step is, so first assume that there are k0, k1, and to kn minus 1, such that k0 times k1 times kn minus 1 is equal to a squared plus a plus 1. And now, in this case, then define kn to be equal to a squared plus 3a plus 3. And so, first of all, this is clearly greater than 1, because in here, a is definitely non-negative, and a non-negative number plus 3 is definitely greater than 1. So after this, first of all, the GCD of a squared plus a plus 1 and k of n is equal to the GCD of a squared plus a plus 1 and a squared plus 3a plus 3, which is equal to the GCD of a squared plus a plus 1 and 2a plus 2. Sorry. And so a squared plus a plus 1 is equal to a times a plus 1 plus 1. And so that means that there are 0 factors of a plus 1 in the left-hand side, and compared to the right-hand side, so this is effectively also equal to the GCD of a squared plus a plus 1 and 2. And after this, you can also see that a times a plus 1 is always even, and 1 plus an even number is always odd. And so that means that the GCD is equal to 1. And since a squared plus a plus 1 was equal to k0 times k1 times kn, kn minus 1, that means that kn, GCD of kn and ki for I less than n is always equal to 1. Because the GCD of their product and kn is also 1. And so now we also have that k0 times k1 all the way to times kn is equal to k0 times k1 to kn minus 1 times kn, which is equal to a squared plus a plus 1 times a squared plus 3a plus 2. And so now this term is obviously equal to a squared, a plus 1 squared minus a, and this term is equal to a plus 1 squared plus a plus 2. And so if we expand this out some more, we have that this is equal to a plus 1 to the 4th plus 2 times a plus 1 squared minus a squared minus 2a. And so after this, you can clearly just see that this is equal to a plus 1 to the 4th plus a plus 1 squared plus a squared plus 2a plus 1 minus a squared minus 2a, or a plus 1 to the 4th plus a plus 1 squared plus 1. And now this is clearly in the form of a prime squared plus a prime. Okay. I'll redraw that. A prime squared plus a prime plus 1, where a prime is equal to a plus 1 squared. And so what that means is that the inductive step holds true, and so that completes the question. So does anyone have any questions on any of the problems?